Electromagnetic comes from two words, electro, which has to do with the electric field or movement of electric charges, and magnetic from magnetic field. How do we define electromagnetic induction? It is a phenomenon where a changing magnetic field or flux under suitable conditions induce electric current in a conductor. It was discovered by Michael Faraday and has led to the large-scale production of electrical energy in all the power stations. Now, having defined this technology, let's now talk about induced electromotive force. Induced electromotive force. For there to be induced electromotive force, there are conditions which must be there. This condition is such that there must be relative motion between the conductor and the electric field, between the magnetic field and the conductor. How can we have relative motion? We hold a magnet stationary and we move the coil, or we hold the coil stationary and we move the magnet into and out of the coil, and by so doing, you will be changing magnetic field or flux linking the conductor. Now, whenever EMF is induced in a conductor, it causes induced electric current. There are factors that affect magnitude of induced EMF. These are the factors. Number one, rate of change of magnetic flux linkage. And we said that for there to be induced EMF, there must be a magnetic field or flux linking the conductor. The rate at which this field changes will affect the amount of induced EMF. And you find that the amount of induced EMF will be increasing with the increasing rate of change of magnetic flux linking the conductor. The second factor is the strength of magnetic field. How do we vary the strength of magnetic field? We use the electromagnet, and around it is the solenoid. So when we change the current in the solenoid, in which we have the soft iron core, then you vary the strength of the electromagnet and hence the electric field. And therefore, the amount of induced EMF will be increasing with the increasing strength of magnetic field. The third factor is the number of turns in the coil. And you find that EMF is induced in each turn of the coil. The larger the number of turns, the higher the induced EMF, because cumulatively, if there are so many turns and in each turn is induced EMF, put together, there is higher induced EMF. Let's now talk about Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction, EMI, abbreviation for that. This factor, this law is coined or comes from the factors that we talked about, especially the first one, which is the rate of change of flux linkage. So we say the following, that this law is stipulating that the amount of induced EMF will be varying in proportion to the rate of change of flux linkage. So then how do we state it? This law states that the amount of the magnitude of induced EMF is proportional to the rate of change flux linkage, which means the amount of induced EMF will be increasing with increasing rate of flux linkage. So that is the statement of Faraday's law of electromagnetic induction. Again, I repeat, it states that the rate of change of the magnitude of induced EMF is proportional to the rate of change of magnetic flux linkage. How to address that? We move to another concept, Lenz's law. Now, this law is used to investigate the direction of induced current, and the following setup will be used. This one is a coil. This one is a coil, and we have galvanometer. There's a magnet. The magnet is moved into the coil. Realize the following. This is a north pole of the magnet advancing into the coil. According to this law, a north pole must be created here at this adjacent end of the coil to oppose the incoming north pole. And therefore, for this north pole to be formed here at this particular end, the flow of current in this particular coil should ensure that a north pole is created here. According to clock rule, current must be flowing in the anti-clockwise direction at this end of the coil. So this is how current will be flowing at that particular end of the coil. Again, it is the correction here. There is an advancing north pole. A north pole must be created so that the flow of current in this particular coil produces a north pole, and therefore, according to clock rule, current must be flowing in anti-clockwise direction at this particular end. And therefore, a north pole is formed here. Now, if the magnet is being withdrawn from the coil, you can use this diagram here. North, south. Now, the magnet is being withdrawn from the coil, and as we said earlier on, as we withdraw the magnet from the coil, a south pole must be created here to oppose the outgoing north pole. And therefore, according to clock rule, current must be flowing in clockwise direction at this end, so as to create a south pole, and therefore current flows this way. Now, the flow of current in this direction will make this galvanometer to deflect in this direction, and the flow of current in this anti-clockwise direction at this particular end will cause this particular pointer to reflect towards the left. And therefore, for the diagram here, for the first diagram, As the north pole of the magnet is moved towards the coil, the induced current flows in the coil, forming the electromagnet, with the north pole at the end nearest the incoming magnet, opposing the movement of the magnet. When the magnet is moved away, like in this figure here, figure B, is moved away, we're saying that the induced current in this coil must create a south pole here to oppose the outgoing north pole. And therefore, the flow of current in this coil at this end adjacent to this outgoing north pole must be in clockwise direction. That you check at this end, current must be in clockwise direction. Whenever it happens, then the current reflects towards the line. Then how do we now state this law? We state this law in this manner. We say that the direction of induced EMF is such that the induced current which it causes to flow produces a magnetic effect that opposes the change causing it or the change producing it. Again, I stated in this law, says that the direction of induced EMF is such that the induced current which it causes to flow produces a magnetic effect that opposes the change causing it or producing it. And this particular law is in conformity with the law of conservation of energy. Now, let us move on and talk about another concept, determining the direction of induced EMF in a straight conductor. We use Fleming's right-hand rule. Fleming's right-hand rule, also called the dynamo rule. In Form 2, we learn about Fleming's left-hand rule. But now in Form 4, Fleming's right-hand rule, also called dynamo rule. In Fleming's left-hand rule, we were talking about the conductor carrying current in a magnetic field, and motion is caused by that conductor. It moves. That's according to Fleming's left-hand rule. That a conductor carrying current, whenever it is placed in a magnetic field, will experience a force and that it moves. That is the motor rule, also called Fleming's left-hand rule. Now, Fleming's right-hand rule, also called dynamo rule, is such that whenever there is motion of a conductor in a magnetic field, then there will be induced EMF in that particular conductor, causing induced current. And therefore, we shall use the following diagram to illustrate Fleming's left-hand rule. This is a U-shaped magnet. This one is a north pole, south pole. The field moves from north pole to south pole. That is magnetic field. And there is a conductor that is cutting this field. This one is a conductor. It is cutting magnetic field. To show that it is current flowing with this conductor, there must be a galvanometer. So we have connecting wire, then a galvanometer. We have end A and end B. Now, this conductor must be moved perpendicularly to the field, so it can be moved up, so it can be moved down. So, how do we illustrate? Move the wire AB up, perpendicular to the magnetic field, and note the direction of flow of current. Now, in demonstrating Fleming's right-hand rule, also called diamond rule, we have this setup. We have a U-shaped magnet, north pole is here, south pole is here, so the field moves from north to south. We have this conductor AB that is cutting the field, and to show that current is flowing in this conductor, we have a galvanometer connected to this conductor AB. So move the conductor AB up, perpendicular to the field, then move it down. Again, the movements must be perpendicular to the magnetic field. Now it is observed that when the wire moves upwards, the induced current flows from B to A, and when the wire is moved downwards, current moves from A to B, consistent with Fleming's right-hand rule. Now the direction of induced current in this conductor AB is determined by Fleming's left-hand rule. How do we state it? We must hold the first two fingers of the right hand and the thumb mutually at right angles. The first finger, second finger, the thumb mutually at right angles. Bearing in mind that this rule is used to indicate direction of induced current in such a way that the first finger shows direction of the field, the thumb shows the motion of the conductor, then the second finger shows direction of induced current. So how do we state Fleming's right-hand rule? Such that if the thumb and the first two fingers of the right hand are held mutually at right angles, with the first finger pointing in the direction of the field, the thumb pointing in the direction of motion of the conductor, then the second finger shows direction of induced current. As we illustrate, that if this thing is moved upward, this conductor AB is moved upward, the first finger shows field, then the thumb shows motion is up. Then current must flow from B to A. It is moved up. Well, this conductor AB is moved down. Again, the first finger shows field. Now, the thumb shows motion, then the current must be flowing from A to B. That's what I have said. When the wire is moved upwards, the induced current flows from B to A. And when you move downwards, it flows from A to B. And you say that the direction of this induced current in this conductor is summarized or can be determined using Fleming's right-hand rule, which states that if the thumb and the first two fingers of the right hand are held mutually at right angles, with the first finger, this one, pointing in the direction of the magnetic field, the thumb pointing in the direction of motion of the conductor, then the second finger points in the direction of the induced current. And this way is consistent with Lenz's law. That is a very key thing. And the next concept that we shall tackle in today's lesson is mutual induction. is normally used in the transformers, both the step-up and step-down transformers. So whenever there's a coil, there are two coils adjacent. Let me draw some diagram here and you can use it. Whenever there is this coil called the primary coil, and this one here, there is a switch, there is a power source of EMF, and there is a rheostat to vary the strength of current. This is the input coil called the primary coil. Then we have an adjacent coil called the secondary coil. To prove that current is flowing in this other coil, we have a galvanometer connected to it. Now, mutual induction is whereby a changing current in the primary coil produces a magnetic effect in the primary coil which links to the secondary coil, inducing EMF in the secondary coil, which causes induced current to flow in the secondary coil. So you're saying it is the effect caused when a change in current in a coil induces an EMF in another coil close to it. Now, if the two coils are put together, then changing current in this primary coil, how we change current? By the use of a rheostat. So we switch on the circuit, then change current slowly, very slowly using a rheostat. Then that constitutes changing current. And in Form 2 we learn about anytime there is a flow of charges in a conductor, then there must be magnetic field around it. So this change in current in this coil will cause changes in magnetic field. Whenever there is a change in magnetic field, which is linking the other coil, EMF is induced in this secondary coil, causing induced current to flow. So you're saying, if the two coils are close together, then changing current in the primary coil, this is the input coil, also called primary coil, produces a magnetic field which links the secondary coil, inducing EMF in the secondary coil. So the concept here is current flows in the primary coil. This current is varied in steps. The variation in current in the primary coil will cause change in magnetic flux or field, which links the secondary coil, also called the output coil. Whenever there's induced EMF in the output coil, then we are going to have induced current flowing, and therefore it will be shown by the deflection of the galvanometer. So, in that case, we are saying when the switch is closed, this switch is closed, the current in the primary coil will increase from 0 to maximum. Initially, when it is open, 0 current is flowing. When the switch is closed, current in this input coil, also called primary coil, increases from 0 to maximum. And therefore, say maximum value within a very short time. When it happens that way, we will say the magnetic flux in this primary coil linking the secondary coil will increase again from 0 to maximum. That increase in magnetic flux or field in the primary coil that links to the secondary coil will cause induced EMF in the secondary coil. This concept of saying is used in the transformers, both step-up and step-down transformer. So when the magnetic flux linking with the secondary coil changes, an EMF is induced in this secondary coil, causing a current flow in the same coil and therefore deflection of the galvanometer. Now, as we finish, how do we change the current in the primary coil? By switching on and off. You switch on and off. When you switch off, then no current flows. You switch on, it moves from 0 to maximum. Number 2, vary the current using a rheostat. This is a rheostat. It's a variable resistor. You can vary current using it. Number 3, by using alternating current in the primary coil. So using AC can also cause a change in current in the primary coil. And this change is very important. It will cause changes in magnetic field, which is making the secondary coil cause induced current. Now, how do we increase the output? EMF, which means EMF in the secondary coil. There are 3 ways of doing that. Number 1, winding the primary and secondary coils on a soft iron core, which will concentrate the fields within the 2 coils and therefore causing maximum linkage. Number 2, by having more turns in the secondary coil. And as we said, EMF is induced in each turn. So if there are so many turns, then we are going to have larger or high induced EMF. Then lastly, winding the secondary coil on a primary coil to ensure maximum flux linkage. Thank you very much for attending the lesson. God bless you.